Okay, we start. Yeah. So the menu. Let's see how far I get. Yes. Let's see how far I get. But today the intention is to to continue our discussion last class that we were talking about petroleum fiscal systems, and then about NPV calculations, just to give you a rough idea how these calculations are made and what do they contain. And then we are going to go to one application example of actually Monte Carlo, okay, to handle how do we handle uncertainties when we are estimating either volumetric volumes of oil or gas in place and also total recoverable reserves. So let's see if not, we leave part of it for tomorrow. Just something before we start. The exercise is already published in its final form, except I guess some bugs you will find along the way. Okay, but it has 4 problems, and problem 2 I'm going to explain. Maybe you already have the tools from before. You saw it in another course, especially those of you taking petroleum economics, the course that I mentioned. You will know how to make it, but I'm going to give a very quick orientation how it is made. Then problem 3, it's about the second part of the lecture today, or we will see. I guess it's going to prolong to tomorrow. That you have to calculate the original oil in place for this reservoir, Kobe, and the total recoverable reserves. That's problem number 3, and you have to do quite some cases there. And number 4 is to basically, you don't have to do it, but you will have to say, if you are going to solve problem 3 using probability 3, how will you solve it? Okay? But you don't actually have to solve it, because there will be many factors, parameters, and then the tree, if you remember my comment last class, it becomes very, very large, okay? Because you have to account for all the possibilities, which is basically the number of parameters for each variable, and you have to multiply, so if you have many layers, that becomes too big. And that's what will happen in this problem. But so you have to explain how will you solve it, and of course you have to discretize each parameter and to find the 3 values that you're going to use. Okay, but it's ready, and the deadline hasn't been set yet because there are some things that I haven't covered, but probably will be by mid or the end of the month. Okay, usually after I cover everything in the lecture, that you have enough tools, enough knowledge to solve it, from that point we give 2 weeks to make it. Okay, and some people they have been asking if if a group of 4 is allowed. Okay, there is nothing wrong with that, or up to 4 is allowed. But the thing is that I think 3 is a good number where all of you have to work. Okay, 4 sometimes one of you is like the taking notes or doing the report, is not doing actually the scientific work. Okay, so if you are 4, I will say just make sure that all of you participate and know what each one is doing. Yeah, and all of you are in charge of some technical part. Because some will say, okay, I'm the guy that makes the report, I'm the making everything look nice, but you're not really involved, and then you have a disadvantage when you go to the exam. There was also another question last class that you're very concerned about digital exam, especially those that had it before, had a very bad experience with it. The digital exam, my idea is that we will make it with Excel. Okay, the same tool that you will be working with along the whole semester. So it shouldn't be, that's what I expect. Okay, maybe I'm too optimistic, but it shouldn't be so traumatic for you. Okay, but if you have very strong resistance, if you have some very strong comment opposition, I suggest that you convey it to the reference group. We have them here. Just lift your hands. We have 1, 2 members here. Okay, Petra is not here. And then you tell them that you are concerned, that you don't want to have it or something, and then we can have, a talk later in the semester. Okay, but we will try to do our best. I know it's something pilot, it's a new thing, so but the idea is that you will use the same platform that you have been using along the semester. And then it becomes very important, this issue that I told you. If you're working for, so make sure that all of you participate in the process. Yes. Okay, so let's go back to very briefly, okay, to what was missing last class. So we said petroleum fiscal systems. So basically, if you remember, we had a concessionary system where which is very common, and is in, you have it in a lot of countries in the world, and basically you are the owner of a production license. The government gives you the right to that area that you have. You can perform exploration, but you have some limited time. You cannot sit on the license forever. Okay, you have to take action. You have actually to develop the field. And then you have to pay, the idea is that you pay a royalty no matter what, and that royalty is paid in cash. And then you have to pay, you can discount the, let's go very quickly. You can discount the OPEX, and if you have any special payment for loan payments, dividend payment, etc., depending on your agreement. Okay, and then that's the amount that you are going to tax at the end. Okay, based on that, that's what you call the taxable income, and based on that, you take out, and that can be split in different ways depending on the country. You might have a regional tax, you might have a national tax, you might have even a like a regional tax. Okay. While you have some other type, which is called like sharing contractual systems. And the main idea here, the main principle is that the company, you are a contractor for the government. You are making the development of the field in behalf of the government. And you have here two main schemes. One of them is a service contract. And here basically the company gets paid certain fee. They agree on a fee. Okay, I'm going to pay you so much money for this amount of work for along these years. And you have a contract, and you don't have anything to do any involvement with the production. So this is paid in the developing and operating company. In cash. Okay, they are paid in money. That doesn't depend. Maybe at some point the field is closed. Maybe they might have an agreement in the contract that if it's closed, they don't pay. But if some cases might not be producing, and the company still has to receive everything, that fee. Okay. And then you have production sharing contracts. Okay, also the abbreviated PSC. And in these arrangements, the company gets paid in production. Okay, you are assigned a production share. Okay, and the main difference is that the government gets its share in production, oil and gas production. Okay, they are the ones that take it to the tanker, take it to the market. They are going to make sure they are going to sell it. They don't trust or they don't want to give it to the company to sell it. Then the government is an equal partner in the development of the asset, okay, in the development of the field, and in the development and operation so they can really affect all the decisions in the operation and the development of the field. They have more power to decide. If they feel very strongly that something shouldn't be done in a certain way, the enhanced recovery strategy they have, the platform concept they have, maybe they want to, you know, to make the company exploit the regional system when they have, for example, a very strong concrete industry. So they say, well, let's go for this platform which is concrete based and not go for anything else. So they have really power to control how the asset is going to be developed. Okay, so some countries, I'm going to list some of them here. So for example, Malaysia, India, Nigeria, Angola, Trinidad, Egypt. Okay, just some examples. And the way you calculate is that you have the total production of, let's say, oil and gas, okay? And we take from here a percentage, which is the royalty. That we always have to pay, a royalty to the government. But in these cases, usually the royalty is much smaller than in concessionary systems. Then we have, again, what we call the net revenue. And then we take out everything that has to do with the expenses, okay, what we call the deductibles. That I think that's the word we used last class, right? That is the OPEX, depreciation, amortization. Maybe you have also dividends here. And then you have what is called the profit production. Okay, and here is that you have splitting the cake. Depending on the percentage each one has in the production sharing contract, you might have 3, 4, 5 different partners. Okay, you have a percentage for partner 1, a percentage for partner 2, and a percentage for the government. And each one of them gets their share in production, okay, in oil and gas. Okay, that depends, split on the share. Okay, and after you have that, then what do? That's the amount I use to calculate the taxable income, right? This consists on the taxable income. And after that I have to calculate the tax. And here I have at the end finally the net cash flow. Okay? So you have, it's very similar, but you have first the splitting in production before you go to calculate the tax. Okay? So really the main point to convey here is that be careful, you might have all variations of these two systems, okay, different variations on different agreements in the contract, but the thing you have to remember is how the cake is split, okay, and what kind of subtractions you are taking along the process. Okay, here you have royalty, the deductible, you are doing it anyhow, and the tax. Okay, but the way they are calculated is different in the production contract and also in the concessionary. Okay, but we are not going to be, that's just to give you we are not going to be calculating tax. That being said, we are not going to be including tax in our calculations. Okay, I think it becomes a bit more messy, some more things that you have to carry, and at the end, you know, doesn't give you anything in addition, but you have to remember it. Okay, so you have to be careful to take it into account. Okay, so let's go to these NPV calculations very quickly. So NPV stands for net present value, and like I mentioned earlier, NPV is usually the main number, not the only number, but the main number people use to decide, you know, on different production strategies, on different production systems, on different platforms, on different options. They use the NPV, the economy of the project, as the main indicator, decision variable. But you will see we need quite a few things to populate that NPV. So that's something that becomes available only when you have enough information about the system. Maybe at an early phase you have no idea when the project will be realized, so you have to use a proxy, or you have to use an approximate number to give value to the project. So this I have to, so let's put here just a disclaimer. There must be a minimum of information to be able to compute NPV. Okay? Because the way that it works is that I'm going to sum the cash flow for each year. Okay, so I have, let's make it here every year, and of course we make, usually the accountancy is made by the end of the year. So this here means end of year, and here we're talking project years, end of project year. Okay, and we start of course with the end of year 1, end of year 2, 3, so forth. Okay, and we have to calculate the cash flow in each one of these years. Okay, let's call it CF1. Okay, and that's nothing else than the sum of all the revenue minus all the expenses that happen on that particular year. Okay, revenue from year 1 and expenses from year 1 also. But the thing is that, so the NPV really is just like a sum of those numbers, so all of the cash flows along the years. The thing is that you cannot sum, like probably all of you know, you cannot sum money that happen or that I get or is taken from me in different points in time, because they have different values, right? Due to inflation, due to different things, but the money in 10 years won't have the same value that the money today. Okay, so you have to make a discount before summing all of them up. You have to put them at the same reference. All the money has to be taken to the same reference, and in that case, usually the reference is year 0. Okay, project start. Let's put it here. Okay. And what you do is that you calculate the discounted cash flow, and that will be CF1 divided by 1 plus the year where you are, okay, that I'm going to call it I, to the power, the discount rate or the inflation rate, like you say, how the money changes its value with time in every year, to the power of J, which is the year. Okay, year measured from, can you see there? Yeah. Yeah, in the back. Can you see this small font? Year measured from project startup. And this I is called the discount rate. Okay, and that we can relate that to the inflation, but we will see is slightly different. Each company, they have a rate that they use depending on what they have experienced. Okay, it's not that they use the inflation from the country. They use okay. So the money in the future, it will be worth less or more today? Less. Less. Okay. That's saying just that if I have, for example, $10 here, it will be worth much less today. Okay. If I receive the money 10 years from now, it will be much less today. Okay, due to this, the change in the inflation. So after I have all of that, then I can calculate the NPV, which is just the sum of all of the numbers in that cell, okay, for the whole project duration. So let's make that equation here. NPV is just the sum from year I'm using J, okay, equal 1 to N, where N is the total number of years, of the cash flow in each year cash flow in J divided by 1 plus I to the power of J. Okay, if you want to make it very compact. Yes? Okay, and then so what have we learned? That what kind of expenses we have. So here we have to put some more columns, okay, to put all the expenses and all the revenues. Okay, expenses, for example, we have, what do we have in expenses? We have capex, okay, and we use that unit is US dollars. Drillex, and that also we use, sometimes we use millions, US dollars. What else? We have OPEX. What else we have? ABEX, that's not usually included when I'm, in the field development process. Huh? Then I should have the taxes, okay, and royalties that we are not going to discuss here. We're not going to take them into account. Okay, and then I have the revenues, okay, which I will only have when I have production, right? The revenues. So we should have one more column here that is called production. I'm going to call it just QO or Q gas. Okay, and of course you should have one with the price, right? So didn't leave enough space. Okay. So that roughly said, that's the way you compute the NPV of the project. You have to make, for every year, you have to calculate the expenses minus the revenues. That will be given in dollars of that year, so don't be confused. That will be given by whatever dollar you had to pay year 1, 2, 3. And that gives you the sum of all of them. That will give you the total cash flow. And that's the plot that I mentioned yesterday, that it looks with time the cash flow. Okay, initially I have seismic engineering studies. Okay, so it's becoming heavier. Then I have paying for the facilities, paying for the offshore structure, the installation of the pipeline, drilling the wells. I'm choked. Okay, then I have some other expenses. I'm having putting everything ready for operation, paying for the salaries of the people, paying for the operators, etc. Okay, and then at some point I start having some production. Okay, so it start getting less negative, and then the revenue starts getting positive. Okay, bigger than the expenses. At the end, I don't have, after I start producing, usually I don't have that many big expenses. I have done all my expenditures usually before that. Okay. Yes, and then that happens. So here will be, for example, 0 during the first maybe 5, 6 years, and then I start having some number here. And I do that for the whole life of the project. Okay, I do it for 30 years, 20 years, whatever my field is supposed to produce for.
Excuse me?
Yes?
Can you just explain for us this I and J, what it mean, how we can use it?
The I is the discount rate that I told you is like the inflation. If you have an inflation in the country, for example, of 3% or 4%, a gallon of milk that costs $10 next year will cost more. Okay, will cost, for example, $11. Okay. So that's this I that you have here, and J is just the number of years measured from the startup. Okay, so if you're the end of year 1 will be 1. Okay, end of year 2 will be 2. Yes.
Is this discount rate fixed?
Yes, the discount rate, you have to make sensitivity on it. The company internally, they manage a number that if they had money and they put it in some fund or they invested in the future, or for different projects they have different interest rates. Okay, so you have to choose one for their, when they make the evaluation. But usually it's like the oil price. You make a sensitivity analysis saying how that's going to affect your project. Okay, usually something between
It's
7
like
and
one number, not a function of years.
no, usually it's one number.
Does it vary with countries?
Yes, with the company usually. Not,
countries?
huh?
Not within countries?
Yeah, it might change, but usually it's the company that takes the decision which rate to use. Okay, and they might say, I have a portfolio in Asia and I use a number. I have portfolio in the US, I use another number, but it's the company that at the end they decide, depending on past experience. Yes?
In the plot, is it cumulative cash flow?
No, that's cash flow with time.
Okay. So it's when you haven't started production, it will go down until it's not cumulative. So I thought that would be like a build-up of expenses.
No, well, for example, here, let's say you are paying just for seismic, okay? And here you're paying just for exploration wells. Here you're paying for offshore structures, okay? And here you're paying for the salary of the workers that are ready to work, okay? So that gives you always negative because so far you have no revenue. When you start putting 1 well, 2 wells in production and selling that, you start gaining some revenue, but it's very small, okay? And at the end, when you start in full production, let's say here you have already all of your wells operating, you have to subtract just the OPEX, which might be very small, okay? And at the end, that's what, and maybe, you know, if that depends on the price, okay? This depends how the price fluctuates every year, okay? If the price is fixed, that means that your production profile here, it does basically the same, has roughly the same shape, okay?
But some of the expenses are always present, like the workers.
Yeah, that's in OPEX, okay? So OPEX, you won't have any OPEX initially, okay? But when you have production startup, then you start having OPEX. Yeah, but that's what I'm saying. That usually is very small compared to the revenue of the field. Mm?
Are salaries considered as OPEX?
Yeah.
So you'd still have salaries in the beginning stages, like.
No, but this OPEX is salaries of the operators, of the workers. All the other salaries are engineering hours, are, yeah. So it's OPEX usually is considered everything that has to do with the production phase. Mm. Yes?
Which oil price do you use when this is for an end of the year calculation?
That's
And the rates also. Which rate do you use?
yeah. Usually, people use a fixed price. Okay, you assume because there is no better method. Okay, people say during all years it's going to keep the same, or it's going to increase with the inflation, with some inflation. You have that is detailed in the compendium. Okay,
Yep.
if you want to read more about it. Let me give you the page exactly. There are two basic methods, but there is yeah, this here, this section 14.2.1. So you read on that, but basically there are two methods. One of them you keep it constant during the life of the field, and the other one you start changing it due to the inflation, increasing it due to the inflation. Okay, but you know that's some people say, and that's still kind of a discussion. They say, what if we use a more realistic price change? Okay, we use some historical change. If we use some variation every year, but that's very unpredictable. How is it going to change? So who says that using something constant is going to be better than using some variation? Okay, so for simplicity, people use a number and then they change it up and down to see how that affects your NPV. We have actually one project that is looking, a PhD project that is looking into that to see how that actually affects at the end. How do I operate my field? If, for example, maybe in those years that you have a very high oil price, you will produce more and maybe produce less. But yeah. Okay, clear, more or less, very simplified. Who is taking? I think he's sitting there in the back, taking petroleum economics, so you can give some more spices, some more complex, but in basics, fundamentals, that is it. Okay, summing all the income on all the expenses on 1 year, having them on a column, you have to discount that number, take it to a common reference, and then you add all of them up. Okay. you have also something called the IRR, okay, that is called the internal rate of return. So let's see here. I usually depends on the company, but usually it's a number between 7, can be all the way to 10%, but it's usually between 7 and 8. Then you have the internal rate of return. That is another number that we look at to see how robust our project is. And we say, is the discount rate, that means the I, that gives an NPV of 0. So if you make some variation, NPV versus I, that usually, if the project is how you say, is profitable, it will be positive here, maybe 7-6%, and then when you start increasing it, 12, okay, it becomes, at the end, at some point, it goes to negative. So that's the internal rate of return, and that's another number that is sometimes used for to take decisions, to characterize a project. So what is better, that is higher or is lower? Huh?
Low.
Higher.
Higher.
We have now. Who says higher? Yeah, lower. Now we need the other ones that didn't vote it to see what is the truth. Okay, if it's higher, that means that the project is more robust. That you can have a stronger devaluation of the money.
Yeah.
Okay, and we will still be positive. Yes. Okay, so that's everything you need for your exercise. You can start working on it. But let's go through the text a bit to clarify, if there are any questions. So you're looking at this Goliath field. These calculations are very simplified, but I have tried to make realistic values. Okay, so I have tried to take as much as possible information from documents, the public domain. So you say the field will be produced in plateau, 100,000 barrels per day, and that's how the production profile looks like. So actually you will be producing for 1.5 years until you start and enter the decline phase. You're using so remember, capex, so we need in that capex many different things, okay, but we are going to assume here that really the main bulk of the cost is the cost of this, okay, the platform, the Sevan platform itself, the processing facilities, the risers, everything that this has inside, okay. Then we have another big cost, which is the Drillex. So to make it simple for you, I just say, remember the Drillex depends on how many days you have used to drill the well, because you have a vessel, okay, you have a boat drilling the well, and that vessel, if it has problems, it has to stay longer, and then it will cost you more. Then you have the equipment that you have to put inside the well. Yep, and the Christmas tree. So here I say, to make it simple, each well cost perforating, the test, completing, well equipment is 120 million each well, and I don't make any distinction between producer and injector, okay, which is not exactly correct, but an approximation to make your life simple. Be aware that here you have an annual constant increase of 5%, and I don't call it actually inflation, because the price of the well really doesn't depend much on the material. Okay, basically it depends on the demand for the vessel in a certain region. Okay, if you have a lot of drilling activity around the world, then you have less vessels to fulfill that activity, so then the price goes up. If you have less drilling, then You have more vessels free that you can use. But I'm saying the increase is 5% on that. Okay, so if you can drill. Okay, you have to drill these 22 wells in 4 years. Okay, so you have to split. It doesn't give you a round number, but you can say 6, 6, and then the rest 5, 5 and 5. And the wells drilled in year 1 will cost 120. Wells drilled in year 2 will cost 5% more. Okay. Yeah, that's the capex. OPEX is 100 million per year. And you have to decide, usually that number, should increase also with inflation, should increase also with time. But I leave it to you how to take that number into account. So you decide what to do with it. So you have to make your cash flow, okay, and you say from here, where at least I have to make for 15 years, and then I have to make the development before that. Okay, so you say here, I say that 4 years for drilling, the platform will be delivered in 4 years. So I will say you have to start, it will be at the end 19 years total the project. Okay. And after you do that, you calculate the NPV. I think that's the discount rate is 7%. The oil price is 60. And then you have to make a variation of what happens if the oil price goes up by 40, down by 40%. The well cost, the drillex will go per well plus minus 30%. The capex plus minus 30%. OPEX plus minus 30%, and delay of the production in 1 and 2 years. For some reason I had a problem. I could not drill I could not tie, for example, a flow line. I could not drill in the time I expected. So how that's going to affect my project, to have delayed revenue. And you have to plot your results in a tornado chart, just like if you were going to make it for a PDO. Okay?
Which tornado chart? You covered it before?
The tornado? Yes. Yeah, tornado chart is the one that it looks like. Okay, you have the base NPV, and you have here an axis that goes positive NPV and probably very negative NPV. And then you make the variation, for example, on the oil price. If I now assume that the oil price is, we said 30%, no, 40%, right? Yeah, so how much is 40%? $56 per barrel. And then 40% less, that's how much? 24? 24. Okay, and you put the NPV of those two options. Okay, see which one has the biggest effect. And also for other factors, for capex. Okay, clear on that problem? Yes. Expenses per year, if you, like I say, at the end of the exercise, the cost, everything is very simplified. You're assuming that each well just have a fixed number. You're not including the rig time. On the capex, we're neglecting many different things, the engineering time. So it's a very simplified analysis. So if you feel like you want to improve it, or you find a number doesn't click, or you find something, you're welcome to change it. Okay, this is just the starting base. I initially put here, it had a sentence to say that you have to digitize this figure, but I have, if you go to the Excel sheet that is provided for that, you will see that the production is already given. Okay, so you don't have to make that homework. But if you know, I'm sure maybe you will need it in the future. So it's called Web Plot Digitizer. It has moved. So it's this page. And here you can load any image that is a graph, okay, a plot, and from there you can extract and steal the points and use them for your work. Okay, so that you won't have to do it in this exercise, but I just want to include it here because that's a very useful engineering tool. So to take points and you don't have to have anything installed, you can use it from your browser. Yes?
The cloud digitizer is also very good.
Hmm?
Cloud digitizer.
It's also good?
It's a very around 200 kilowatts. That's very good.
Okay. Plot digitizer.
Yeah, fine. I could check it on my laptop.
Yeah, you send me later the link. Any question before we take a break? No? About the exercise? No? Have you already started working on it?
No.
Yes? Okay, I have some yes, some no. So, okay. I think they already have started having sessions. The assistants last week. Did they have one? No. No. Okay, so maybe they will have it tomorrow. I think from 12 was the session. Okay, and for those that have the what is it, the drilling well stability, you will have a special session on Thursday, right? Or
It's on the same day, just later.
later? Okay. Okay, so let's take a break. Let's say 10 minutes, and we come back for the second part of the class.
Yeah, that's what I wanted to say.
Okay, remember the discounting, we do it only to be able to sum money from different years. Otherwise, it won't make sense. Okay, so to be able to put everything on the same reference, which I use the year 0, and then I can sum all of these numbers up. Okay, that's the only reason. And like the oil price is very different. For example, maybe you have a very strong inflation one year, and it might be much higher than 7. Maybe one year is much better, you have less. So that number also might fluctuate with time, but there is a big uncertainty associated to that number that you don't know how it's going to behave in the future. If it's going to increase, it's going to decrease. So when you are in the evaluation phase, you just say, well, to make it simple, I just keep it constant, and I increase, decrease to see its effect. Okay, many things we do, just the complexity, you also have to be a bit pragmatic. Okay, the complexity, you can add it only if it's going to give you something back. Okay, if it doesn't give you much back, or if it's going to be a mess to analyze the results, maybe you don't use it. Okay, there was a guy in a book I read, was a guy modeling reciprocating pumps. He said sometimes a simpler model with the proper assumptions is better than a more complex model with all the wrong assumptions. Okay, when you start adding, and that's very true, when you start adding a lot of things to a model and a lot of variations, you have to do it such that you're going to get something back. Okay, that will be, if you have to assume all of these parameters, then might not be worth it. Okay, so before we go, okay, so now let's talk about this example we have. Okay, so you will have NPV is very important. This course is not about economy, but we have to mention it because it's one of the main indicators we use to take decisions. Okay, NPV. But I don't want to go too much into it. There are software. If you are going to, to work on that in the future, you're going to get specialized training. But it's just to show you where that magic number came from. Okay, in which we based our decisions on. Okay, and in a very simple, basic way, this is everything it's done. So it's, in a way, it's also very simplistic. Yeah. So let's go now to the so let's say I will call this quantifying uncertainty. Using Monte Carlo method. And for that, we are going to take one very specific example, something that companies have to make during the issuing the PDO. I guess you have read, all of you have read the Hebron PDO. So it's probabilistic estimation of hydrocarbon volumes. Remember, that's one of the big numbers. That gives me the revenue right away. How much hydrocarbon I have in place, okay? But that's not the only factor. I also want to know how much I can recover from what I have underground, and how much I can recover, and I call that total recoverable reserves. Okay, and let's go very quickly to this Hebron PDO. Okay, and what we are going to make, it's a very also simplified, but also an approximation of what they are doing in this part. Reserve estimates. Okay? And if you want to see kind of more detail how, a more realistic case, how it is done, I recommend, if you haven't done it already, to read that section, section 5.1. Okay, like that's a suggestion. That's from the Hebron PDO. Okay. Yeah. So I discussed last class, when we usually don't have just one unique value, right, of a parameter, of a variable. We have maybe a range. Okay, for example, for all of these, let's talk specifically. So to calculate, so first, which letter do we use for hydrocarbon in place? If you remember, huh?
N.
Okay, N is for oil. So it's let's call it oil in place. Okay, we call it with the letter N, right? And that's just the integral from 0 to time end. No, that's not, right? N is just how much we have in place. We also have some other names we use are original oil in place, right? Or initial oil in place. And for gas, is G, okay? Original gas in place and initial gas in place. Okay. Now, that's, as I told you, that's not exactly what we produce, right? What is that? What we produce at the end?
Recovery profit.
Huh? Is what? How did we call it last class? NPU, ultimate cumulative oil production, right? And that's how that's related to N with the recovery factor. Okay, so how much I produce divided by how much was originally in place. Here is that I get the ultimate recovery factor. Right? Yeah. So what you will have to make in the exercise 2, actually you have to compute both NPU and N with some uncertainty in the input. Okay, you have uncertainty in the input, you're not exactly sure what value you're going to have, and you will have to, you will have to calculate, with using Monte Carlo method. Yeah, and let's make it also for gas. Okay, and for that we are going to use a very simple calculation. So the parameters that we are going to use a formula. So it will be NPU, or also called total recoverable reserves, right? And that will be equal to the total rock volume that we have. Okay, we say we're approximating maybe a reservoir like a cylinder, where I have an area at the top and it has certain thickness. Okay, so in that case my rock volume will be just area times the H, right? Now, not only that's not completely oil, but only the spaces within the pores are filled with oil, right? So what else do I have to?
One minus saturation.
Saturation is one thing, but first it comes porosity. Okay, so the porosity, if you remember, is the pore volume divided by the total volume. Okay, and then I find with this one is the total available pore volume. Then we have exactly what you said. In the space between the pores, you might have different things. You might have water, might have gas, might have oil. In our case, for our particular example, it's an undersaturated oil reservoir, so we have no gas, just water. Okay, so we multiply times the saturation of oil, or 1 minus the saturation of water. Okay, and then what else do we need? We also need something called net to gross. Okay, and that is because from this area H, or this length H that I have, not all of it's reservoir bearing rock. Okay, not all of that is filled with hydrocarbon. If we may put a logging tool through it, maybe we will see that it has a structure. Like here I have hydrocarbon, maybe it has some slabs that have shale, then I have some other layer which is hydrocarbon rock bearing, hydrocarbon bearing rock, and then so forth. Okay, so what I say net to gross is actually how much of the vertical distribution is field has reservoir, hydrocarbon bearing reservoir, right? Okay, so that's okay. What else do we need?
Formation volume factor.
Okay, that's very important. Okay, and that's what I told you. This gives you the volume you have under the ground. Okay, but it's not the same. We are not selling it under those conditions. We have to take it to surface conditions. Okay, and as I told you, if you have to also remember something, you will have to remember many things. But one thing from this course, this fluid properties is extremely important. Okay, it's not something that you can just say, I use a number and that's all, because it's a multiplier. So where do I put that VO? Is oil, called oil formation volume factor, and that gives me volume in the reservoir divided by volume at standard conditions. Okay, P standard condition and T standard condition. What are those numbers?
1 atmosphere and 15.
0.325 bar, right, and 15.56 Celsius, right? Okay, and that we call BO, and that we just divide, right? To get NPU should be always in standard cubic meter or in standard barrel. Okay, but now that's how much we have in place that we take to the surface. But really from that amount, I won't be able to recover everything, right? Just a portion. That I define that by the recovery factor. Okay, so now I have to put the recovery factor here. Yes? And that's the equation you are going to use for the task. And I'm going to speak later about what happens when you have a more complicated case. But if you assume we were very lucky, we had a very simple reservoir structure. It almost looks like a cylinder or like a box. So then this approximation becomes okay, right? I have no objections. When your reservoir starts becoming more geometrically complicated, is split in different parts, then you cannot use this simplified approach. Okay, you have to use something more complicated. Okay, but if you see from here, we have exactly what we had for Monte Carlo, right? What is my input? My input is rock volume, right? Then we have porosity, oil saturation, net to gross. What else? BO, right? And the recovery factor. And all of that goes into one calculation that is an equation, okay? It's a function, let's call it the function. And in this function, the function is called the estimation of NPU, right? And then at the end, I get NPU. Okay? And now the thing is that we don't have, because nothing in this world is perfect, only a few things. We don't have a unique number for each one of those. We actually have a range, right? That's in the basic, the starting point, we have a range, a minimum and a maximum. Minimum and maximum for all of them. That they can come, for example, from when I made the exploration drilling. Okay, when I make coring and then I found, well, the saturation in this well was so much, the saturation here was so much, so there you get the two bounds. Okay. Also fluid sampling with this method that I mentioned last class. Okay. Check, I think I'm forgetting something. Yeah. Okay, so for example, this rock volume, I'm going to put it here in red, comes from drilling, okay, exploration drilling. Okay, and also it comes by the structure that you think how the reservoir is. Okay, so here also the geology, the regional geology is playing a role. Okay, and also yeah, here you don't have much okay. Porosity, where is porosity coming from? Again, also exploration drilling. And logging, okay, and also coring, okay. And if I have less and less information, I have to rely more on correlations. Maybe for a certain region, maybe depending on the how do you say, some other parameter like cuttings. Okay. So if I don't have enough data, then I have to start using an equation, using a correlation to try to determine that. So say from cuttings, correlation, oil saturation, where from? Logging. Anything else? Coring. What else? Net to gross? Logging. Nowhere, no other place. BO. Fluid sampling. Okay, that we usually make with this DST, drill stem test. Recovery factor. Lab test, one part. Then we have expert, right? Previous experience. Yes? So you see all the different things, and there might be much more that we are neglecting, but all the different uncertainties, or all the different, first the source of that number and how, how it came to be. So it's not one unique number, but it's basically a range. Okay, and that's what we have. And we have usually a lot of uncertainty. Like here I have the total uncertainty. It's yeah, but is for all of them is between the range of plus minus 40%. Okay, and especially you take the sample in one place and you don't know exactly if the same thing applies, all around. So the way we do that, it's like I mentioned last class, we make a probability function of each one of the parameters, okay, which describes all of you know probability function. Yeah, PDF, probability distribution function. So usually we use a probability to describe the input parameters that are uncertain. And that basically just indicates in the y-axis it has the probability of occurrence, and in the x-axis it has basically the variable, the values of the variable. Okay? And you have the maximum and you have the minimum. Okay? And it might be, if, for example, I ask you, what happens if every, I have no idea. I made just 2 samples of porosity, and then I say, well, I have no idea how it is in between, in the whole field. What is the best to use? Everything has the same probability, right, of occurrence. I have no idea, I have a minimum and a maximum, but I don't know really which one is more likely. So in that case, I just say, well, basically all of them have the same. I just managed to find the minimum and the maximum. But all of them, everything in between, has the same probability of occurrence. Okay, so that's what I call a rectangular or a uniform distribution. Uniform probability distribution. Okay. There are some other distributions, like for example you have other types. Let's put here. The triangle distribution. But for example, if we talk about porosity, you have mean, max, and then you have one value here which has the highest probability. Okay, how do we call that number? Go back to your high school years.
Expected value.
The expected value, but it has a much nicer name. The mode. Okay, much shorter. The mode. Okay, and that tells you basically that there is one. Well, it might go, porosity might go to a maximum or might go to a minimum, but really it prefers, is more likely that it will be around that number, right? Around this number, around the mode. Okay, so how do I get, you say, well, how do I get that kind of distribution? How do I get more like a more detailed distribution? I can make it by getting more information, okay, collecting more field data. Okay, for example, I drilled 20 exploration wells. Okay, the first one, maybe the porosity. Okay, let's say, for example, more exploration wells. Okay, let's say I drilled 20, right? So that's the porosity. The first one, the porosity maybe was here. Second one, the porosity was here. Okay, third one, porosity was here. But then after, it will start maybe to become a bit close. They will start to repeat themselves. So I will have more and more occurrences. So that will be the number of occurrences. Okay, we'll have more and more occurrences of one particular porosity and not so many from the rest. Okay, yeah, so that's one way. I just gather more and more information. The problem with that, in field development, that's expensive. Okay, I have to get it from coring, I have to get it for logging. It's an operation that is time consuming and is expensive. Okay, what is the other source of, how can I make my distribution better? Correlation, that's one option. Okay, but we can call it, I say, the expert. Okay, someone that can make a better interpretation or a more solid interpretation with the data that you have. Yes? We're just about to finish, so be a bit patient. Okay, so going back to our problem, okay, that's the problem we have. Here we know we have an equation, right, in this box inside. So how are we going to say all of them have a distribution associated that I provide in the exercise? So how I want to here not to have just one unique number, but I want to have also a distribution. And we will see later tomorrow how do we deal with this distribution. But we want to get the same, right? If all of them are like that, I want to get also here a distribution, something that tells me what is the mode, most likely expected value, my maximum, minimum. So how do I do that, from this scheme? For that I run what I mentioned last class, Monte Carlo, right? So what are the steps of Monte Carlo? Okay, what was the first step?
Get the distributions.
The distributions, let's say we have them, okay? The distribution for each one of the parameters. Let's say we have, for this one is uniform, for this one is triangular, for this one looks something like that, this one is also uniform, this one is also triangle, and for this one is like this. Okay, let's say I have the distribution. So what's the first step?
Get the base case.
Random sampling. Okay, I'm going to take a random, and we will say it's not exactly that random, but we are going to take a sample, random sample from here, from here, from here, from here, for all the input variables. Okay, so take a random sample of each input variable. Okay, then process number 2, a number. Okay, a random value is, if we say the porosity is between 18% and 20%, I just take 18.5, a random number, completely random from the top of my head. You can take 0.17, okay? You can take any number. Then second step, we compute, right, in a deterministic way, our compute NPU, right, using the equation. What is the third step? We have to save, right? You have to save the result and repeat from 1, okay? Okay, let's say go back to 1. I have to take another random number from that distribution. I have again to compute the NPU, and then I have to save the result. And I have to repeat that, okay, for, let's say, a certain number of iterations. So we have to make it more computer friendly, okay? We have to think now in terms of a computer. So we say if the number of iterations is less than the number of iterations maximum, okay, 1000, then I save the result and repeat from 1. And let me put it here. Okay, not here. Sorry. Okay, else, if I have exceeded the number of iterations, what do? I go to step 4, which is not end, but is process the results, right? Actually make this frequency diagram. It's called make the frequency diagram, okay, or the PDF with the results saved. Okay. And at the end you will see, for at least for this example, you will see something like that, where you have the NPU, and here you have the probability of each NPU. Okay, so these are the 4 steps you have to make, and the limitation really of the Monte Carlo method is how long those steps to make, okay, take. If it takes 10 hours and you have to run 1,000 iterations, then it's not very practical. It will take a lot of time before you have a number, before you have a solution. If it takes, like in our case, a fraction of a second, then you can run with no problem. So before we leave, let's say, how are we going to solve it in Excel? Okay, in Excel we are going to have 3 columns. Okay, we're just about to finish. Porosity, what else was it? Rock volume. This doesn't have any units. Rock volume has in barrels. Okay, that's a unit in volume. Then we have saturation, again doesn't have any units. BO, that which units does it have? Okay, in theory it doesn't have any unit, but it has in reservoir barrels over standard barrels, right? Because it's still barrels, but it's barrels at different conditions. Then we have, what else? Net to gross. Okay, that also is a ratio, doesn't have any units. The recovery factor also doesn't have any units. And at the end we have, so all of this is the input. And here we have, in a very single cell, we have the output, which is NPU, and that is in standard barrels. Okay. So what we are going to make, here we are going to say number of iterations, right? Here we have 1, 2, 3, 4 in Excel, 5, 6. We're going to take one sample, random sample here for all of these parameters, and we are going to compute NPU. Okay, and then we are going to get another random variable here, and then we are going to compute NPU, and so forth. We are going to repeat that. The exercise asks for 1,000 iterations, okay, 1,000 simulations, and then we are going to make the probability analysis on these results, the frequency on all the NPU calculated. Okay?
Given this maximum and minimum
we will see now how exactly how we're going to take that random value. Yes. Okay, depending on the distribution. For example, in this a triangle, should I use this number and this number? They have 0 probability, right, of occurrence. But I can use a number that is just very close to it, like 1.0001. That I can use, okay, greater to that. But in reality, I won't use that. But if I have a rectangular distribution, should I use the values at the edge?
Yeah.
Because they have a how to say, a non-zero probability. Yes?
This might be a obvious question, but when you pulled out a random set of numbers, do you mark them so that you don't pull them out again?
No.
Okay, so you can do the same case several
Yes,
times.
you could have in one universe that you have, if you believe in these things, the coincidences, you might have 2 cases that are the same. Okay, but that's why you have to have a really good random number generator. Okay, but we will see how we are going to do it tomorrow. We are going to solve at least one case of those that you have to make tomorrow. So I will say we close the session today. So remember, for tomorrow I would like if you can bring your computers. We're going to work on this problem. Yep. So just to summarize, finally we got rid of the economy. You already got an idea how it is done. And we start looking at this problem, which is reserve estimate and total recoverable reserve. And we set up how we are going to solve the problem, and actually tomorrow we are going to solve it. Any question before we close? No? Okay. See you tomorrow.
I just wanted to know, do you use a portal?
Sorry.